When we gaze up at the night sky, we are peering into the vast expanse of the universe. But what we see is just a tiny fraction of what's out there. We call this the observable universe. It's like our own cosmic bubble, centered on us. Imagine a bright light bulb suddenly switched on. The light from that bulb takes time to travel outward, reaching us after a certain delay. The observable universe is similar. It's the region of space from which light has had time to reach us since the Big Bang. This means that the farther away we look in space, the further back in time we are seeing. The most distant objects we can observe are those whose light has been traveling toward us for almost the entire age of the universe. Beyond that distance lies a mysterious realm we cannot yet see. The edge of the observable universe is not a physical boundary, it's simply a horizon beyond which we cannot currently see. As time passes, more of the universe will come into view as light from more distant regions finally reaches us. However, there's a catch. The universe is expanding. The expansion of the universe adds another layer of complexity to our understanding of the observable universe. As the universe expands, space itself stretches, and this stretching affects the light traveling through it. Imagine a wave on the surface of a pond. As the wave travels outward, its wavelength increases and its energy decreases. Similarly, as light travels through the expanding universe, its wavelength is stretched out. This stretching of light waves is called redshift. Redshift is a crucial concept in cosmology because it tells us that the universe is expanding. The farther away a galaxy is from us, the more its light is redshifted, indicating that it is moving away from us at a faster rate. This expansion has profound implications for the observable universe. As the universe expands, some regions are moving away from us faster than the speed of light. Since nothing can travel faster than light, the light from these regions will never reach us, no matter how long we wait. This defines the cosmic horizon, a boundary beyond which we can never receive information. The cosmic horizon is constantly expanding as the universe ages, but it also means that a significant portion of the universe will forever remain hidden from our view. While we cannot see beyond the cosmic horizon, we can detect faint whispers from the early universe. This faint afterglow is called the cosmic microwave background, CMB, radiation. It's a faint glow of microwave radiation that permeates all of space. The CMB is a relic from a time when the universe was much hotter and denser, just a few 100,000 years after the Big Bang. At that time, the universe was filled with a hot, dense soup of particles and radiation. As the universe expanded and cooled, this primordial soup thinned out, and the radiation was free to travel through space. Today, this radiation reaches us from all directions, providing us with a snapshot of the early universe. The CMB is remarkably uniform with a nearly identical temperature in all directions. However, there are tiny temperature fluctuations within the CMB, indicating slight variations in density in the early universe. These fluctuations are the seeds of the large-scale structures, such as galaxies and galaxy clusters, that we observe today. The CMB provides strong evidence for the Big Bang theory, and has allowed cosmologists to determine the age, composition, and geometry of the universe with remarkable precision. However, the CMB represents the limit of our observations. We cannot see beyond this point in time, leaving many questions about the true nature and extent of the universe unanswered. The concept of an infinite universe is both awe-inspiring and mind-boggling. If the universe is infinite, it means that it extends forever in all directions, with no edge or boundary. This idea has profound implications for our understanding of space, time, and our place in the cosmos. One of the main arguments in favor of an infinite universe stems from the concept of curvature. The shape of the universe is related to its density. If the universe has a high enough density, it would be curved like a sphere, and if you travel far enough in one direction, you would eventually end up back where you started. However, observations suggest that the universe has a very flat geometry, meaning that it's either infinite or so large that its curvature is undetectable on the scales we can observe. This flatness, combined with the lack of any observed edges or boundaries, lends credence to the infinite universe hypothesis. The idea of infinity is challenging to grasp. It means that there are potentially an infinite number of stars, galaxies, and even planets out there. It also raises the possibility of other forms of life, perhaps even civilizations far more advanced than our own, existing somewhere in the vastness of the cosmos. However, the infinite universe hypothesis is not without its critics and challenges. Some argue that the very concept of infinity is problematic, and that the universe must have some finite size. even if it's beyond our current ability to observe. To make sense of the universe on its grandest scales, cosmologists rely on a set of fundamental assumptions known as cosmological principles. These principles are based on the idea that the universe is both homogeneous and isotropic. Homogeneity means that the universe is roughly the same everywhere on large scales. In other words, if you were to zoom out far enough, the distribution of matter and energy would appear relatively uniform, regardless of your location. Isotropy means that the universe looks roughly the same in all directions. This implies that there's no preferred direction or center of the universe. From our vantage point on Earth, the universe appears isotropic, as evidenced by the uniform distribution of galaxies and the cosmic microwave background radiation. These principles are supported by numerous observations and form the foundation of modern cosmology. They allow us to develop models and make predictions about the universe's behavior on the largest scales. However, it's important to note that these principles are based on observations made within the observable universe. We cannot be certain if these principles hold true beyond the cosmic horizon. It's possible that the universe exhibits different properties on scales larger than we can currently observe. Despite these limitations, the cosmological principles have proven to be powerful tools for understanding the universe and have led to significant advancements in our knowledge of its origin, evolution, and ultimate fate. The idea of an infinite universe has profound implications for our understanding of the cosmos and our place within it. If the universe is truly infinite, it challenges our notions of uniqueness, rarity, and even the meaning of life itself. One of the most intriguing implications of an infinite universe is the potential for an infinite number of inhabited worlds. If the conditions for life arose on Earth, it stands to reason that they could arise elsewhere in an infinite universe, given enough time and suitable environments. This raises the possibility of alien civilizations, some perhaps far more advanced than our own, existing somewhere in the vastness of space. The sheer scale of an infinite universe suggests that we are unlikely to be alone, making the search for extraterrestrial life a compelling and potentially fruitful endeavor. However, the vastness of an infinite universe also presents a profound philosophical challenge. If the universe is infinite, it means that everything that can happen will happen an infinite number of times. This includes the formation of stars, planets, and even life itself. This raises questions about the uniqueness of our own existence. If there are infinite versions of ourselves out there, living out every possible permutation of our lives, does our individual existence hold any significance? These are just some of the philosophical and existential questions that arise when we contemplate the possibility of an infinite universe. While we may never know for certain whether the universe is truly infinite, the very act of pondering such questions can deepen our understanding of our place in the cosmos and the nature of reality itself.